Hey, welcome to Let's Get to the Marks, going through GCSE Combined Science Trilogy paper, higher tier paper 2, 2019. There's 7 questions, 1 hour and 15 minutes. What I suggest you do at the start of each question is you press pause on the video, grab some pen, never heard of that, grab some paper, grab a pen, have a go at the questions, and then unpause and watch the walkthrough. If not, you can just do it in your head, but make it active. Okay, water, let's go. Oh, by the way, another point, if you're there and you're a separate scientist, don't get all snobby like, oh, I can't do the combined paper. Every question on the combined paper could come up in your separate chemistry exam. So if you're a chemistry GCSE student, I highly recommend doing all of the combined papers. You'll be far better prepared than someone who just does the chemistry papers. Okay, water that is safe to drink contains dissolved substances. What do we call water that is safe to drink? Is it desalinated, filtered, fresh, or potable? You might have heard of this before. It is known as potable water. It means the water you can pour from your tap into a pot, and that is safe to cook with and to drink. Desalinated is when you remove salt from water. That doesn't make it safe to drink. It could still have bacteria and stuff in it. You can filter water to get rid of certain hard salts and substances, but it could still have bacteria. Doesn't make it safe to drink. Fresh water out of a river could have bacteria. Doesn't make it safe to drink. Only potable water is safe to drink because it has been sterilized with ozone, UV light, or chlorine. 1.2, describe a test for pure water. Give the result of the test if the water is pure. So there are some tests for water. One is to test, do you have water? And that is the old using anhydrous white powder, copper sulfate, add water, it goes blue. They sometimes ask that. But this is saying about purity. How do we know water will be pure? The idea is you boil the water and measure the boiling point. Obviously, heat the water, measure the boiling point. The result, it should boil at exactly 100 degrees. So if it boils at an exact temperature, and it doesn't just have to be water, it could be ethanol, it could be chocolate, whatever. Well, not chocolate, that's a mixture, but it could be any pure substance. If it boils at an exact temperature, then it is pure. If it boils over a range, so if it starts bubbling at 98, but the temperature still rises until 105 for water, then that is not pure water. It has other things in it. So pure substances boil at an exact temperature. That is their boiling point. Right. Or you could do melting point, freezing point, whatever, but I'm going with boiling point. Right, 1.3, describe a method to determine the mass of dissolved solids in 100 centimeter cubes of river water. This is one of those mental, experimental think through ones. Why don't you pause the video, have a go? Okay, I'm going to go through the answer. So you've got your water from the river and we want 100 centimeters. How are we going to make sure it's 100 centimeters? I'm going to say, and they might not have this on the mark scheme, but I'm going to go for it anyway. Measure out 100 centimeter cubed using a measuring cylinder. You could use a volumetric flask if you like, but that would be my opening point. Measure out 100 centimeters using a measuring cylinder. Weigh, yeah, I don't want to say weigh. Let's go record the mass of our empty, oh my gosh, empty beaker. So you want to record the mass of an empty beaker, not an empty beaker, but there we go, I can't spell. So record the mass of an empty beaker, then add water to beaker, heat the beaker. What are we going to heat it with? We're going to heat the beaker with a Bunsen burner. You could gently heat it with a water bath. I'm just going Bunsen burner because I can't draw a water bath, but I can draw a Bunsen burner. Look, wow, look at that artwork. Awesome. Look, there's the fire. Oh, he's heating on a yellow flame. That's not good. Okay, add the water to the beaker, heat the beaker with a Bunsen burner. What's going to happen to the water? Think about it, folks. What's going to happen if you heat that water? Well, eventually all of the water is going to leave the beaker by evaporation. Keep heating until all the water is gone. Now, how do we know all the water is gone? Well, you can look with your eyes, but also the mass should become constant. So you can do what we call heating till a constant mass. We could heat this every minute, reweigh the beaker, heat for another minute, reweigh the beaker. Once the mass no longer goes down, I mean, you can visually see all the water's gone, but then you can still heat because there might be some water you can't see mixed up with the solid. Once the mass doesn't change, you know all the water has left. Okay, now what we want to do is measure the mass of beaker and minus the mass of the empty beaker to find mass of solids. So you might think, again, let me just visualize that for you if you like it visualized. So what I'm saying is we recorded the mass of the empty beaker. Do you remember we said at the start, record the mass of the empty beaker? We've then evaporated all of the water from our beaker and we have the beaker with solid. So we now have some white solids in there. How do I know they're white? Well, they're probably going to be because the water is colorless. So we've got some white solids left over. You're then just going to minus the this from this to find this. So if we take those away, we're going to end up with the mass of the solid, right? And that's what we're explaining there. So there we go. That's going to get us all of them beautiful 4 marks. Okay, 1.4. A sample of river water contains 125 milligrams per decimeter of dissolved solids. Calculate the mass of dissolved solids in grams in 250 centimeters of this sample of river water. Give your answer to 2 significant figures. It's worth 4 marks. Let's go, peeps. Okay, first thing to do, you might be like super frightened of this, but this comes up in paper 1 or paper 2 every time, and we can kind of spot the type of calculation it is. And if you work through all of my walkthroughs, you will get used to seeing this question come up and you'll get used to knowing, aha, this is what I've got to do. And so as we read through, what we're going to do here, folks, we are going to go, what is milligrams per decimeter? So when you see like mg per decimeter, what is that? That is the concentration. And so if we look at the next number, it has centimeter cubed at the end of it. And it's just one number with centimeter cubed. What is centimeter cubed? That is the volume. And like I say, once you get practiced at doing these questions, first time you do it, difficult. Once you get practiced at them, you'll start to get used to it. And then the question is actually asking, calculate the mass. And that is symbol M for mass. And that should trigger you to go, oh, there's a triangle. I know this off by heart. And if you don't, put it on a revision card. You need to learn it off by heart. It's the key to you getting full marks on this. So it's mass over concentration times volume. Now, we've got to give the answer to 2 significant figures. So even if we fluff up our calculation here, you still get the marks for doing it to 2 sig figs. Why don't you have a go at this with a pen, paper, and calculator, obviously, and then watch the explanation. Okay, I'm going to go through the explanation, so you should pay attention. So volume is normally in decimeters. Concentration is normally in grams per decimeter, and mass is in grams. So we need to make sure our units have been converted. If we just did concentration times volume, so you're going to cover the M up, and that leaves you with, in order to work out M, I need to do C times V. And you can see we've identified C. And so if you did 125 times 250 and you round it to 2 significant figures, you would get 2 out of 4 marks. The problem why you won't get all 4 marks is because they're not in the correct units. So we need to change the volume, right? We need to change this 250 into decimeters. Now, 1 decimeter is 1,000 centimeters. So we need to divide by 1,000 centimeter cubed, and that will give us 0.25 or 0.250 decimeters. Okay, so we've got 0.250 decimeters, and that is our volume. Now we need to convert the milligrams per decimeter into GDM3 because we don't use milligrams in chemistry normally unless specifically asked. We have to turn it into grams. So how do you turn milligrams into grams? Well, you're going to divide by 1,000 again, same thing. So 125 divided by 1,000 is going to give us 0.125, and that is going to be grams per decimeter. That's not milligrams per decimeter, that's grams per decimeter. Okay, and then all we need to do is times these bad boys together, and that is going to give us our mass, and our mass is 0.3125. We need to round to 2 significant figures. 2 significant figures, we don't count the zeros, so we're looking at the 3, 1, 2, and 5. Now, we want to put two of those numbers down. We're going to put the 3 down. Then we look at the 1 and we go, are we moving the 1 up to 2 or are we keeping it at 1? Well, the number next to it is a 2 and it's not bigger than 4. It's not 5, 6, 7. So we're going to keep it at 0.031. That was the worst explanation of rounding to two significant figures in the world. And by the way, folks, this over here is, not that it matters, that was us converting from milligrams to grams per decimeter. Anywho, there we go. That would get you to 4 fat bad boy marks. Oh my gosh, the question that never ends. 1.5, a water company allows a maximum of 500 milligram per decimeter of sulfate ions in drinking water. Okay. A sample of drinking water contains 44 milligrams per decimeter of sulfate ions. Calculate the percentage of the maximum allowed mass of sulfate ions in the sample of drinking water. So what is the percentage of this, of this? So it sounds harder than it actually is. We just want to go 44 divided by 500 times 100. So calculate the percentage of the maximum allowed mass. So we're going, oh my days, 44, what's going on with the calculator? 44 divided by, calculators had it, times 100 equals 8.8. And here we go. That's the end of that question. Okay, this question is about atmospheric pollutants from fuels. 2.1. Fuel burns in a car engine. Describe how oxides of nitrogen are produced in a car engine. Why don't you pause, have a go? Okay, let me go through the answer. Here is our incredible drawing of a car. And there is the exhaust. And essentially, what happens is nitrogen, whoa, and oxygen are found in the atmosphere. The atmosphere is about 78% nitrogen, 21% oxygen. In goes the nitrogen. Now the engine gets really, really red hot. Check out that engine. That looks heavy. Right, the engine gets red hot, and the nitrogen and the oxygen react together to form nitrogen oxide, and the nitrogen oxide comes out the exhaust. And that is why it's an atmospheric pollution, because that goes in there. And there's even a little equation for this. And it's like this. Hopefully they don't ask for that in the next section, because then I've just given you the answer to the next question. But it goes N2 plus O2 goes to NO2, and we'd need to balance that. So I would need to put a 2 there to make up for that, and that would make 4 oxygen, so the 2 there. And that would be the equation. So what do we want to say? Rather than all my whiffle, waffle, waffle, we want to say nitrogen and oxygen from the air. You could use the words atmosphere. Nitrogen and oxygen from the air, from the air, react on the hot car engine. Oh my gosh, engine. To make nitrogen oxides. There we go. Now, we could just say high temperatures rather than hot car engine. People might think that's a more technical term to use. But so nitrogen, oxygen, the key is that they're from the air and they react under high temperature. Okay, let's move on. Otherwise, we're going to be here all day doing this paper. 2.2. Why do I get a bad feeling? Oh my days, 6 marks, that's why. 2.2, table 1 shows the carbon footprint during the manufacture and use of 3 cars. We've got car A, car B, car C. Mass of CO2 produced during manufacturing kilograms. So we can see that it looks like car C makes the most CO2 when you're building the car. But then the mass of CO2 when driving, it actually releases the least when driving. Total mass of CO2 produced from manufacture and driving in kilograms. Okay, so this kind of produces more CO2 altogether. Total mass of CO2 produced from manufacture and 100 kilometers of driving. Now, if you keep the car for a long time, this is less detrimental to the environment and greenhouse gas causing than car B. Evaluate the carbon footprint of the cars. Use the information from table 1. So what we need to do is we need to evaluate the carbon footprint of the cars. So we just want to say like car C during manufacture produces the most CO2 in kilograms. So that's a good thing to say. And then we want to compare that, whereas car A produces the least. Car A produces the least CO2 per kg. Okay, or CO2 in kg. In kg in manufacture. So we're making the car. If they're not sold and they sit there, car A is the most green and therefore is better for the environment. However, the mass of CO2 produced when driving, actually, car A produces the most CO2 when driving, and car C the least. So they completely swap places when you're driving them. Okay. Now, what we do find is that if you only have the car for a few years or make short journeys, oh my gosh, what is going on there? If you only have the car for a few years or make short journeys, what we can definitely say is that car A produces far less CO2 in manufacture and driving for up to 40,000 kilometers. So like basically, if you're not driving the car a lot, if you're just taking it to the shops every now and again, you're not going on big journeys, maybe you'll only do 40,000 kilometers over 5 years or something, you're not using the car a lot, then car A is definitely the way to go, because look, it only makes 18,920 compared to 24,760 for car C, and car B is a little bit more. However, if you're using the car on long journeys, we start to see that car C is becoming a much more viable option, because the increase from 40,000 to 100,000, so you're doubling the distance. With these guys, you've gone up like 30%. With this one, you've only gone up like 10-15% in CO2. So we can presume from that if you went to 150,000, this would be the best. By that point, it would give out the least CO2. So I would say, however, for long journeys, car C is better than B, as gives out less CO2 over 100,000 kilometers. I don't mean no one's ever going on a 100,000 kilometer journey, but what I mean is like if you're driving the car a lot and you use your car a lot, car C becomes a better option. And what I would say about the evaluation is, however, we do not have data for even longer distances. Over 150 kilometers, car C will probably be the best, as in have the lowest carbon footprint. Now, with evaluations, you also want to make your choice. So based on the data we have, car A is the best choice for short and long driving. It has the lowest carbon footprint when combining manufacture and driving. Yeah, and there we go. That's what I would do. That is my answer, peeps. I know, disgusting. All right, let's move on, because that was actually causing me pain answering that. This question is about chromatography of food coloring. Food coloring is a formulation. What is a formulation? Well, a formulation is a mixture where the different components are in exact amounts. A mixture where the different components are in specific or exact amounts. So it might be that you need 25% oil mixed with 75% alcohol or something along those lines for your mixture, but it has to be specific. 3.2, explain how paper chromatography separates dyes in a food coloring. Do not give the details of how to do the experiment. So how does it separate the dyes in a food coloring? Two ways we can answer this. We can answer this with solubility, or we can answer this with talking about the mobile and stationary phase and affinity for the paper. So I'm going to talk about the easy way with the solubility. So different dyes have different solubilities in the solvent. The more soluble dyes move further in the same time. So that's important as well. If you leave chromatography long enough, all the dyes will reach the end and you won't know that they have different solubilities. But if you put it in for a set time or before the first dye reaches the end, you take it out and dry it, then you will see a pattern. So the more soluble the dye, the further it moves. Now, we could word this in the terms of the mobile and the stationary phase. And if you are somebody who wants to do that, you can say the dyes that have a greater affinity to the mobile phase, which means dissolve better in the solvent, that's the translation, they have a greater affinity for the mobile phase, will move further up the paper in the same time. Dyes that have a greater affinity to the stationary phase, meaning they like to stick in the paper more, will move more slowly up the paper. Anywho, let's zing. Okay, let's get down to the next question. Explain how the student could tell from the chromatogram that the food coloring contained more than one dye. Well, do we actually have a chromatogram? No, we don't. So a chromatogram, for those of you going, what the hell is a chromatogram? Let me show you. Okay, the chromatogram is basically the picture you get. So you start like that with your line and you put your dye on there and then you put a lovely solvent in like that. And as the solvent climbs up the paper, like this, as it climbs up the paper towards the end, what's going to happen is this dye is going to sort of separate out into blobs or spots on the dye. And yeah, we're going to get some different spots. So how can they tell that it contained more than one dye? Well, how many spots are in mine? You have to include the one on the line as well, peeps. Afterwards, you have to, if there's one still on the line, sometimes it moves off the line, but this black color here is obviously insoluble, but essentially this contains four. So what we would say is, how do we know it contains more? There are or is more than one spot on the chromatogram. Oh, it couldn't go any worse. So more than one spot on the chromatogram, multiple spots on the chromatogram. Maybe we need to say more than, oh my days, more than one color. At different distances on the paper. So also maybe I need to mention the word distance, that there's more spots and they're at different places on the paper. That might also be what we need to say there, folks. So just add.
That doesn't matter. Right, let's get on. Let's get on. My camera just bust. Everything went mad. My microphone switched off. Everything had a panic attack. It all went a bit crazy. Okay, explain how the student could use the chromatography to identify unknown dyes in the food coloring. So where was I? Well, that's not going to work anymore because what I was going to do is bring back the old drawing, but that's not going to happen. Right. Okay. What a pain. Actually, what you do, so you might want to pause the video, have a go at this one. Essentially, what you do, this is your chromatogram, and you dip it into some water. That's actually your filter paper, not your chromatogram. And your spots appear. And I'm just going to do like you get like that, and you get like that, let's say. Right, so we got our spots. What we then do is we calculate something called the RF value. So wherever the solvent reaches, we call that the distance the solvent moved. So distance moved by solvent. So you might remember there's RF value, right? So the solvent, which is this stuff, is going to climb up the paper and it's going to go further than any of the colors. Like this is really soluble, almost 100% soluble in the solvent. So it's moved nearly as far as the solvent. Remember the solvent is obviously 100% soluble in itself, doesn't even make any sense, but so it's going to move up the paper. These things are never 100% soluble. They will spend some time stuck to the paper in the stationary phase. So they are coming in and out of the solution and they will not travel as far up the paper. This is very soluble, almost 90%. Now, how do you calculate the RF value, the fraction of solubility there? It's called the retention factor, the distance moved by the spot divided by the distance moved by the solvent. So just to give you an idea, if the solvent moved, let's make it dead easy, right? 10 centimeters. And then let's say this orange spot moved 6 centimeters. If I wanted to calculate the RF value of the orange, I would do 6 over 10 and equal 0.6. So we could say calculate the RF value. And then how do I find out what that is? I look it up in a book or look it up on the internet. You look up and compare to known values. Now, you could take your chromatogram and compare to another chromatogram where they use the same solvent, and you could look and see to identify it like that. But I'm going to use the RF values. So what I'm going to say is calculate the RF value of each spot by doing distance spot moved divided by distance solvent moved. So I've explained how to calculate the RF value, and then I'm going to say, look up the RF value in a data book or compare to known sources. So what I mean by that is compare to ones with known RF values. I might find out that zero point 0.6, that is chlorophyll. Chlorophyll has an RF value of 0.6 when using this particular solvent. So the other thing you could do, if you don't want to answer like this, you could say compare this to a chromatogram of known substances and see if they've traveled the same distance in the same solvent in the same time. Okay, that's 3 marks. Bish, bash, bosh. Right, this question is about copper and fuels. Copper is extracted from low-grade ores by phytomining. Describe how copper is produced by phytomining. You need to know this off by heart. If you don't know it, what I suggest you do is after I've gone through the question, you get a revision card and you write down what is phytomining, and then on the back you put 4 bullet points. Right, I'm going to go through the answer now. So if you've had a go, well done. What you're going to do is you're going to grow a plant and you're going to grow it on the low-grade ore. Ores are rocks that contain metals in them. So you're going to grow your plant and maybe you're going to grow it on some low grade rocks like this, and it is going to suck up in its roots things like lovely copper ions, and they're going to get sucked up in the roots. Then what we're going to do, we're going to burn the plant. I know, pretty brutal, right? You're going to burn the plant, and what you're going to be left behind with afterwards is some ash. You can be left with ash. What does ash look like? Like that, whatever. Then we're going to take the ash and we're going to make a lovely, lovely solution. Like we're going to make it into a solution. And how are we going to do that? We're going to dissolve in water. So we're going to mix it with water and make a solution. And then how are we going to get the metal out of the solution? We're going to do that dreaded thing from paper 1 called electrolysis. You know, that thing where you have the cathode and anode, or you have a positive and a negative electrode. So I'm going to put them there and there. And what's going to happen is that is going to separate out the solution. So we just need to put that into words. There is an alternative. If you don't want to use electrolysis, you can alternatively stick an old piece of iron or scrap metal in here that is more reactive. You can put a more reactive piece of metal, and we call this displacement. And the more reactive metal will push out the less reactive metal, and you will get that metal out. So you can either do electrolysis or displacement. Don't ask me how that looks like displacement, but there we go. Right, so I'm going to put that into 4 bullet points for you. So we're going to say use plants to absorb metal compounds or ions from ores. Then we're going to burn the plant. I'm going to say dissolve the ash, make a solution, use electrolysis or displacement with scrap metal. And there we go. That is really your 4 marks. So use plants, burn the plants, dissolve the ash, and then use electrolysis after making a solution. Bish, bash, bosh. Right, another method of extracting copper from low-grade ores is bioleaching. A solution of copper sulfate produced by bioleaching, that's when you use bacteria and they produce a leachate, has a concentration of 0.13 gram per decimeter. We've been given the relative atomic masses. Calculate the number of moles of copper that can be produced from 1 decimeter of this solution. Number of moles. It's worth 3 marks. Guess what, folks? Guess what? Guess what? Immediately, I'm going through and I'm going, what is that? Well, that, my friends, is known as concentration. Now, do I have to use this? I don't know. That's AR, bit confusing. And that is a volume. So I'm immediately thinking I can do mass, and I might be wrong here. So this is where, oh my gosh, mass over C times V. I've never seen anything as ugly as that. So mass over C times V, like we used earlier in this test. But they've given us MR, and then suddenly you think, oh God, they're giving me MR, but MR goes in the old MR times moles, gives me mass. So it all depends how we're going to do this. Ooh, it says calculate the number of moles of copper that can be produced. So we do need to do the moles. Right, so we need to calculate the mass first and then transfer the mass over, divide it by the MR and get the mole. So we have to use both triangles. Sneaky! Okay, let's go, peeps. They want us to find the mass. Oh no, the number of moles. Moles is N. So that's how we know we had to use this. We've got C and V. C, is it in grams per decimeter? It is. So I want to do C times V. So C is 0.319. Let's times it by V. What is our V? Where's our V? Did I even write down V? I did. It was just squished over here. It's 1 decimeter. So times 1, 0.319 times 1 equals 0.319. And that is grams. So we now have our mass. Now let's transfer over. And if we do the mass over the MR, we get N, which is the moles. We get our answer. So we're going to go 0.319 divided by the MR equals N. I just need to work out the blooming MR. And guess what? They're giving me the ARs. So let's work out the MR. Well, we're going to have 63.5. We're going to plus that to sulfur, which is 32. Which, what does that make? 95.5. And then I want 4 times 16, 44, 60, 24, 64. 60, I'm going to need to calculate, guys. 95.5 plus 64, 64 plus 32 plus 63.5. That gives me a whopping wibbling 159.5. So I actually want to go 0.319 over 159. 0.559.5. I think I said 95. I don't know what I said. 0.319. Oh, geez, divided by answer. My calculator is busted. 2 times 10 to the minus 3. 2 times 10 to the minus 3. What's that in town? That's 0.002 when it's hanging out in town. And that is moles. I use N for number of moles. That was a bit disgusting. Okay. Okay. Oh, geez, Louise. What's going on, Sally? Copper is used as a catalyst. Figure 1 shows the reaction profiles for a reaction with or without a catalyst. So we have a reaction profile and another one. How do the reaction profiles show that using a catalyst does not affect the overall energy change for the reaction? Both reaction profiles show exothermic reactions. They are actually exothermic because energy is lost to the environment, and you can tell that because the product line, what it is this is your reactants before, and that's the amount of energy the reactants have. Then afterwards, the products, whatever you make in the reaction, is lower in this case, and that means some of that energy is all this energy here between this bit and this bit. All of this energy in kilojoules or joules, doesn't really matter what we use, has gone to the environment. So it's been taken away. So let's have a look. Both reaction profiles start at the same energy and end at the same energy. Yes, that is the reason. Because this gap, this number that would go in there, the amount of energy would be the same for each of these because they start in the same place and end in the same place. So that's definitely the one. Boom. Boom. Copper is a catalyst. In a reaction to produce ethanol from carbon dioxide, ethanol is used as a fuel. Suggest why producing ethanol from carbon dioxide is sustainable. So we always worry that producing CO2 warms the environment and causes global warming. So why is it that if we do it from ethanol, we say that overall it's not causing global warming? Where does ethanol come from? So we would say ethanol comes from sugar, which comes from plants, which do photosynthesis. So which comes from, I'm actually talking out my butt here. I haven't even read the question properly. Right, I haven't read this question properly, folks. Come on. Do you know what? Come on, do it now. Arnie, help me out here, mate. This is a real problem. What is going on? This computer is ganging up on me. Okay, let's go. So suggest why producing ethanol. Oh, so they use CO2 to make ethanol. Well, why is that sustainable? Well, CO2 is a greenhouse gas. Um, it is made from plants. No, it's not. It's made from animals during respiration. Um, Yeah, so we don't really have a problem with that. It's a greenhouse gas made from animals during respiration. Um, it is turned into ethanol. When ethanol is burned, it releases CO2. What they're driving at here is why is it okay to use CO2 to make ethanol? Well, it's okay because when you burn the ethanol, you'll release the CO2. So you're using CO2 to make the ethanol, but then when you burn the ethanol, you'll release CO2. So it swings and roundabouts. You use the same amount of ethanol that you make from CO2, you're going to produce the same amount of CO2. Blah, 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 whatever. I just wrote down a load of old junk to do with CO2 and ethanol. Okay, chemistry plays an important role in the sustainable development. What is sustainable development? So, sustainable development is ensuring that future generations have access to resources. So, sustainable development is us using technology without using up all the crude oil. And that means that our children and our grandchildren's children will be able to drive cars and use electricity and do all the wonderful things that we have today, like using smartphones. There'll be lithium still in the ground because we won't have been selfish and dug it all out. So, sustainable development is ensuring, I don't think that's ensuring, that's not how you spell it, right? Ensuring that future generations have access to the same resources we have today. And that is sustainable development. Oh my good gosh, this paper has done my head in. Okay, we're on question 5. This question's about magnesium. A student investigated the rate of the reaction between magnesium and hydrochloric acid. Figure 2 shows the apparatus. So here we've got figure 2. We've got a gas syringe. We've got hydrochloric acid, and we've got a piece of magnesium there. And we can see some bubbles coming off there. Here's a conical flask with a bung, delivery tube, and gas syringe. Okay, let's get into the questions. 5.1, which is the correct ionic equation for the reaction? 1 mark. Why don't you have a go at this? And then I'm going to go through the explanation. Okay, here we go. I'm going to go through the explanation. Seems to be a bit of a crackle on my mic for some reason. I'm not sure, but there's a little crackle on the old MIC. All right, I'm going to go through it. So it says this question is about magnesium. We're looking at the reaction between magnesium and hydrochloric acid. So I'm going to start by writing that equation. What we do is we go Mg plus HCl, and that goes to magnesium. So metal and acid goes to salt and a hydrogen. So we get magnesium chloride plus hydrogen gas. Now, you might be saying to myself, how do I know that it's MgCl2 and not just MgCl? How do you know? Or why isn't it MgCl3? Well, magnesium is in group 2 of the periodic table. This tells me that when magnesium reacts, it becomes a 2 plus ion because it loses 2 electrons in its outer shell. Now, I know that chlorine is in group 7, and this tells me that when chlorine reacts, chlorine becomes a minus ion. It gains an electron to get a full outer shell. Therefore, I know the formula for magnesium chloride. If I have one Mg2 plus like that, I'm going to need 2 chloride ions to go with each. Now, so they cancel out. So the formula is MgCl2. So that was just a little revision on how to work out formulas that you're not familiar with. Now, I need to balance this up. I've naturally got 2 hydrogens because hydrogen is a diatomic molecule. So what I need to do is I need to balance it. I also need 2 chlorines, and we can take care of that by just putting a 2 there. Okay, so this is known as the chemical equation for the reaction between magnesium and hydrochloric acid. Now, we've been asked to do the ionic equation. Now, the ionic equation only shows the ions that are involved in the equation. It doesn't show what we call spectator ions. Now, how do you know what goes on to be included? There are 2 rules, and that is if it changes its oxidation state or its ionic charge, i.e. if it's +1, whatever, then it is included in the equation, or if it changes its physical state. So you can look at it as in physical state. So magnesium is solid, hydrochloric acid is always aqueous. Magnesium chloride that's formed is going to be aqueous because it's soluble. All chloride salts are soluble, and you're going to get gas given off. So anything that either changes their physical state or their ionic charge should go down here. Well, let's have a little look at what changes their physical state or ionic charge. So let's go to it. Right, magnesium, when it's just an atom, it has 0 charge. However, magnesium, when it is an ion in an ionic compound, it has a +2 charge. So it has changed both its physical state from solid to aqueous, and it's changed its ionic charge. I only need one of those things to know that it must be included down here. Then I have our hydrogen, and our hydrogen has gone from aqueous to gaseous, and it's also gone from a +1 charge to a 0 charge. When an atom is in its elemental or covalent form, it has 0 charge there. So it's in its elemental form, so it has 0 charge. So that has changed both physical state and it has changed its ionic state. That looks like an H. That's supposed to be a +1 over here. Ugh, that's even worse. Right, where was I? Yeah, the hydrogen is supposed to be +1 and it's gone to 0. Now you look at the chlorine. The chlorine has gone from -1 and it's still -1 here, and it's aqueous and aqueous. We do not include chlorine. So everything else gets included. Let's go down. Magnesium +2H plus goes to Mg2 plus H2. And that is our bad boy reaction. Why is this not the ionic equation? They included chlorine. Now, chlorine is already -1, and it's -1 there, and it's aqueous there, and it's aqueous there, so we don't include the chlorine. Here is wrong because, again, they've included the chlorine, so they should have got rid of that. And if they got rid of that, then you'd be left with, this would now make it correct because you'd have 2H plus and Mg2 plus, which is what we have up there. And then that one is not correct. It's not even balanced correctly, and it doesn't show the hydrogen either. So yeah, those are all wrong. Okay, that was a long explanation for a one marker, but people find ionic equations hard. Hopefully that's been useful. If it has, make sure you hit the like, peeps. It is a higher level thing. You can still get a level 9 without really understanding ionic equations, although it is helpful if you do. 5.2, what happens in the reaction between magnesium and hydrochloric acid? Electron sharing, electron transfer, proton transfer. So how do we know? Well, what is magnesium? You might want to pause the video, see if you can have a go. I'm going through the explanation. That's a metal. Chlorine's a non-metal. Well, hydrochloric acid is, but essentially magnesium becomes an ionic compound. And of course, it's electron transfer. So it is electron transfer. How do I know that? Well, magnesium is going to give 2 electrons to chlorine. It's going to become +2, and each of the chlorines are going to become -1. So it is ionic. It's an electron transfer. Cool. Okay. Metals and non-metals always do electron transfer. Oh my days. Looks like I'm going to have to do this. 5.3, table 2 shows the students' results. We've got the time in seconds, and we've got the volume of gas being given off. Plot the data from table 2 on here. Draw the line of best fit, 3 marks. You're getting 2 marks for the plots. You're allowed 1 error, and you can still get the 2 marks with 1 error. As long as the error is only one of these baby squares out from where the plot should be, they'll let you have that. All right, let's scroll down a bit so I can fit everything in. There we go. Well, I can't really fit it all in. No, did he? There we go. Okay, let's go. So time in seconds is 0, and the volume of gas is 0. So I want to put a plot here at 0, 0. Then I want 10 along the bottom. Where is 10? It's halfway between 20 and 0 and up to 12.5. Now you might say, well, how do I work what these? You can count. There are 10. That's really nice and easy. This is a nice, easy one. So it's about there. Oof. Remember, I'm allowed to be half out, so we'll allow that one. 35 and 36. Well, 36 is kind of easy because it's just 6 squares above 30. But down here, it's all a little bit more tricky. We've got 5 squares and we've got a value of 20. So what we need to do down here is go 20 divided by 5. Each square, each baby square is worth 4. So if I want to get to 36 here along the bottom, I want to come to 20 and then go 24, 28, 32, 36. It's the line just before 40. So I'm going to take that and take that up to, oh no, we want 35. So it's the line in between there. Sorry, excusez-moi. The line in between 34. These go up in fours. 24, 28, 32, 36. Yeah, it's in there. And then we're going up 35, sorry, 35, 36, whatever, baby. And we're going up to 36 in the volume of gas, which is there. So I'm going to put that right in there. It's hard because each square is worth 4. I mean, that is pretty brutal. Okay, let's zing over to what we got next. We got 50, which is bang in the middle. That's not too bad. I know that one. And 43.5, which is all right because it's 3 and then a half there. So we're starting, it looks like we might be starting to curve. That's that one done. Let's go over here. We've got 95 and 59. So 95, these go up in fours, 84, 88, 92, 96. So again, what a brute. 95 is just before this line here. What disgusting values. And then 9 up. So right there, 95 is just before that line there. So that's 95. Yuck. And then what have we got? 120 seconds and 60, 120 and 60. Now we're leveling out. and then 140 seconds and 60. Now we're leveling out. So draw a line of best fit. Let's change the color, pink and green. Very nice. And let's go like this. Oh gosh, I missed that one. Don't kill me for that. But there we go. So don't worry that I missed that. That's all right. Slight anomalous result maybe, but one, two, three. I'm giving myself three. Why not? If you're marking your own paper, give yourself max marks. Okay, describe the changes in the rate of this reaction. I'm going to go back up and just focus on that word describe. It didn't say explain, so it said describe the changes. Let's see if I can get my little diagram back, which would be lovely if I can. And I can. So let's go down. Oh, Sugar Ray Leonard. No, up. Hey, we're back, people. So describe the changes for 3 marks. You don't have to explain anything, say any reasons. So what are the changes in the rate of reaction? So where is the rate of reaction highest? Well, it's where the gradient is steepest. So we want to say up to 20 seconds, the rate of reaction is steepest. So this is my describe. Um, Rate of reaction is fastest in, but or highest in first 20 seconds as line is steeper. Okay, so there's my description, and that's going to get me a mark. And then what do I want to say is happening like here? After that, look, it's not as steep. The line is curving more. The rate of reaction. So rates of reaction decreases after this um, between say 20 and 80, between 20 and 80 seconds. And that's going to be my second mark. And then I want to say the final mark, the reaction has stopped. The rate of reaction has reached zero at 120. So before that, it's really just after 100 seconds, maybe 110 seconds, something like that. So after 100, let's say, and 10 seconds, the rate of reaction is zero. Um, Line levels off. So it's no longer reacting. So our rate of reaction has reached zero. So quickest at the start, then it slows down, then it reaches zero. And that will get you 3 bad boy marks for the description. And you don't have to explain why. Maybe that's the next question. Let's go down and see what the next question is. Oh, my good gosh. Explain why the rate of this reaction changes. Give your answer in terms of collision theory. So why was it high at first and then lower afterwards? Well, at first or initially, there are more reactants. So more chance, or we can say, so more frequent, whoopsie, successful collisions. So the rate of reaction is high at first because there are more reactants, so more frequent successful collisions. Then it slows down as there are less reactants, so less chance of successful collisions. Successful collisions are ones that are impactful enough and are high energy enough to overcome the minimum energy needed to break the bonds, the activation energy, and cause a successful reaction. So there's less collisions basically. So if you wanted to simplify this, you'd say there's more reactants at the start, so more collisions between particles. Then there's less reactants as the reaction continues and products are made. So there is less chance of a successful collision. And then at the end, when the line is flat, so when the line on graph is flat, which I don't need to say, but all the reactants, whoopsie, are used up. So there are no more successful collisions. You might still get collisions, but not between reactant particles. And that explains bish, bash, bosh, why. That's the explanation. So you're talking about the collisions between the particles, etc. Could use the word concentration. Concentration of reactants is highest at the start, so more collisions. Right, let's get on. Question 6. This question is about oxygen and sulfur dioxide, SO2. So oxygen is O2, sulfur dioxide is SO2. Give the test and result for the oxygen gas. So what is the test for oxygen gas? Well, it relights a glowing splint. I've kind of given it all away in that. So really, I'm going to delete that. So the test is use a glowing splint. Now, if you don't want to say glowing splint, you can say blow out a lit splint. So if you don't want to say glowing, you can just say light a splint, then blow it out. And that is then a glowing splint. Result, the splint relights with oxygen. So the test for oxygen is you put it near the test tube and the splint will relight. So essentially what that's going to look like is you've got your test tube over here, like so. You've got your gas in there. You're like, is it oxygen? So you take your splint and you blow it out. You go, and it blows out. And what you're left with is a glowing splint. Now, what is a glowing splint? Well, a little bit of it will be burnt at the end where the ashes from the wood you burnt before you blew it out, and it will have some red glowy bits. You then place this splint near the opening to this test tube, and if that's oxygen gas coming out, and surprise, surprise, in my little lovely diagram, it is oxygen gas coming out. What happens? As soon as the glowing splint touches the oxygen gas, it's highly flammable. So it relights. Ta-da! And we go, it's oxygen. And there you go. Okay, next question, 6.2. The reaction between oxygen and sulfur dioxide is at equilibrium. O2 gas plus 2 SO2 gas. Reversible symbol goes to 2 sulfur trioxides, SO3 gas. Some of the sulfur trioxide, SO3, is removed. Explain what happens to the position of equilibrium. So a guy called Le Chatelier, no, sorry, that's what I think of him. No, Le Chatelier, he came up with Le Chatelier's principle. And what he said is that whatever you do to a reversible reaction, it will shift its equilibrium to oppose, go against what you've done. It will try and reverse what you've done. It will go oppose the change. So if you make the change by making less, so you make less SO3, Le Chatelier says, no, I'm not having that. I'm going to make more SO3. So it shifts the equilibrium to the right to increase that again so that we get to a balance again. So it always is opposing to try and get us back to balance. So some of the sulfur trioxide is removed. What happens to the position of equilibrium? So you're going to get 1 mark for the description. The EQ, now you can't write EQ in your exam, but I can. So you should write the equilibrium position shifts to the right. So it's going to move to the right. Why? To oppose the change and try and increase the SO3 again. So it's doing Le Chatelier's principle, is trying to oppose the change by breaking down some of the oxygen and sulfur dioxide to make more SO3 because you removed some, you naughty scientist. Okay. We're on 6.3. We're nearly there, peeps. 2 more questions and we're done. 6.3. Sulfur dioxide is an atmospheric pollutant. So something that we're releasing into the air. Sulfur dioxide pollution is reduced by reacting calcium oxide with sulfur dioxide to produce calcium sulfite. So we've got calcium oxide here. What they do in power stations and factories where sulfur dioxide is being released, like from coal factories, in order to reduce the amount of acid rain, because sulfur dioxide causes acid rain, they spray it with calcium oxide. They can spray that up at the flues, the chimneys, and that can neutralize the sulfur dioxide in an acid-base reaction. Sulfur dioxide being a non-metal oxide, which means it's acidic, and calcium oxide being a metal oxide, which means it's basic. You neutralize to make this salt, calcium sulfite. But this is nothing to do with that. This is maths, people, and moles. 7 grams of calcium oxide reacts with an excess of sulfur dioxide. Relative atomic masses of Ar of O is 16, S is 32, and calcium Ca is 40. Calculate the mass of calcium sulfite produced. Lovely and easy, and it's 4 marks. I'm going to show you how to do this one. So we've been given the equation, and what we want to do, whenever you get given an equation, and it's definitely going to be maths because you see numbers everywhere and they use the word calculate, then you want to write the ratios. And notably, this is a 1 to 1 to 1 to 1 ratio. So it's beautiful. We haven't got to do any hard ratio. Now they've given us 7 grams. We ask ourselves, what is grams? Well, grams is known as mass. And so I like to highlight my question. That's an M. Then I've been given MR or AR, MR, potato, patata, potato, patata, whatever. Potato, 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 tomato, tomato. Oh gosh, just rub it out. So, yeah, now that we've rubbed that out, MR we're going to put there. Okay, MRAR, same thing. So we've got O is 16, S is 32, blah, blah, blah. What does this remind you of? This should trigger you. Trigger! Make you think I need to do the magic triangle, and we're going to do mass over MR times moles. However you remember it, mass equals Mr. Moles, or whatever you remember, that is what you should do. So mass is always in grams, moles and MR. Okay, I'm not going to do the units for that. It's just longness. So calculate the mass of calcium sulfide produced. I've got 7 grams of calcium oxide. So this is calcium oxide. Let's work out the moles. So I'm going to go 7G over calcium oxide. Calcium is 40 and oxygen is 16. So 40 plus 16. So 7 divided by 56 is going to give me my moles of calcium oxide. I don't know why this one is 4 marks. It don't make sense to me. And that equals 0.125 grams. Sorry, moles. Going to get myself in trouble there. Now, so that you don't make a mistake and write grams there, because you can forget what you're doing, it's better to put your G there. Then you know 7G. Oh, that can't be G there as well. 7 divided by MR equals 0.125 moles, and I use N for moles. So now we know the moles of calcium oxide. We can look at the ratio and go, how much calcium sulfite can it produce? CaSO3. So it is 1 to 1. So you're going to get a mark for saying, well, it's 1 to 1. So I know that there's 0.125 moles of calcium sulfite. Now, all I need to do is take this in here. Moles times MR gives me the mass. So I'm going to do my MR of calcium sulfite is 40 plus 32 plus 316. The 316! Sorry, that was a wrestler. Yeah. Right. And we're going to times that by 0.125. Lovely jubbly. So let's go, oh my gosh, times, and we're going to go 40 plus 32. What are 316s? That's 48, right? And that equals 15. And the answer is the mass of calcium sulfite produced is 15 grams, 1,5. And so what are you going to get the marks for? Well, you're going to get the marks for doing 7 over 56 and getting that. 1 mark for working out that that is also calcium sulfite because it's a 1 to 1 ratio. And then we're going to do moles times MR. It's going to get you another mark, and getting the correct answer is going to get you the 4th mark. Boom. Okay. We're on to the final question, I do believe. So, question 7, this question's about hydrocarbons and crude oil. Hydrocarbon fuels are produced from crude oil. Describe how crude oil is separated into fractions. This has come up so many times. So, what we want to do here is look at this. This is my incredible drawing, level 2 GCSE art drawing of a fractional distillation column. Am I putting all the bits in? No, I am not, because that's just too long. So different fractions like naphtha, petrol, diesel, refinery gases, bitumen, they all come off at different sections, but we've got to describe how. So first of all, you take your sticky, thick, viscous, black mixture of crude oil and you put it into the tower. What you do on the way in, you heat it, and that is our first mark. So our very first mark is to say, heat the crude oil. Sometimes on the mark schemes, a separate mark is, we'll say, crude oil vaporizes. Sometimes these are on the same marking point and they don't give you a separate mark, but sometimes that's 2 marks. You heat the crude oil, it turns to a vapor. What do we mean by a vapor? We mean it turns to a gas. So now it is a gas. It is going to rise up the tower. I like to write that, but it's rarely a mark. So I'm going to say the fractions, because now it separates into fractions, rise up the tower because they're a gas. So gases rise up, less dense than air, hopefully, or maybe not. But they rise up the tower. And what's next? The tower, folks, is hot at the bottom and cold at the top. A lot of people like to use the term a temperature gradient. So we can say the tower is hotter at the bottom and colder at the top. Now, it's quicker to describe this and say, um, it has a temperature gradient. Now, I've used shorthand there. Don't use that in your exam. So fractions rise up the tower. The tower is hotter at the bottom, colder at the top. That is often a mark for just pointing out that there's a temperature gradient. And then what that means is smaller fractions have lower boiling points. Again, I'm using an abbreviation. So condense higher up the tower. Now, I could have said larger fractions. I could say, oh my days, I could say my spelling is pea poor. What do I mean by pea poor? Well, you can work it out. So smaller fractions have lower boiling points, so condense higher up the tower. There we go. Now, I could have said larger fractions have higher boiling points and condense lower down the tower. Bitumen comes out here, heavy fuel oil, like which they use in ships. And then you have diesel, and then kerosene, petrol, etc. All of that. They come up in a different order based on their size. The bigger, heavier, higher boiling point fractions come out at the bottom. The smaller fractions with lower boiling points come out higher up the tower. And if you didn't want to say that, you could just say different fractions have different boiling points, so condense at different points of the tower. And the key word is they have different boiling points and they condense at different parts of the tower. Heat, vaporize, the tower has a temperature gradient, different boiling points, condense at different parts. Those would be my key points. Right, butane is a hydrocarbon. 2 equations for the combustion of butane are 2 C4H10 plus 13O2 goes to 8 CO2 plus 10H2O. And then we've got 2 C4H10 plus 5O2 go to AC plus 10H2O. Why are different products formed? So what they've done here, little trick question, have they formed carbon dioxide? Normally in combustion, we form carbon dioxide. What isn't there enough of in this second equation? So we're going to say in the first equation, there is a plentiful supply of oxygen. You can basically say there are different amounts of oxygen because there's different amounts of oxygen. So in the first equation, there's a plentiful supply of oxygen. It is complete combustion. Okay. The second equation, there is limited, not enough oxygen. So it is incomplete combustion. I know what you're thinking. Do I have to write all of that for 1 mark? No, I'm just giving you the perfect explanation. You could just say because there is not enough oxygen in the second equation, or there is excess oxygen in the first equation. It is complete combustion and incomplete combustion. You can use any parts of those that will explain it. All right, let's zing on. So we're on to 7.3. I'm going the wrong way. One product of the combustion of butane is carbon monoxide. Balance the equation. So we've got butane plus oxygen goes to carbon monoxide and water. So how you do these combustion equations, leave the oxygen till last. And in any chemical equation, if you have an element on its own, leave that till last. It's the easiest one to balance last. It's just the trick. So what we're going to do is we're going to look how many carbons are here. There's 4. So I need to put a 4 here. I can't get around that. How many hydrogens are here? 10. So I've got H2. What do I need to multiply that by to make 10? I'm going to put a 5 there. Beautiful. Now I'm going to add up how many individual oxygens are here and here and combine them on this side of the arrow. So I've got 4 oxygens and I've got 5 oxygens. That's 9 oxygens. Now, if I write 9 O's, it looks like 90. So I'm going to put the word 9 oxygens. How am I going to get 9 there? There's 2 possibilities. The easiest way is to go 4.5 or 4.5 oxygens. So you can write 4.5. Some people are like, I don't want to use 4.5. No, no. So if you don't want to use 4.5, multiply everything here by 2. So this, you'd put a 2 here, you put a 9 there, you put an 8 there, and a 10 there. But me, I like to use the fractions. Okay. Let's go, let's go. 7.4 peoples, and that's the end of the test. So, carbon dioxide is a greenhouse gas. Describe the greenhouse effect in terms of the interaction of short and long wave radiation with matter. So, 4 marks. Describe the greenhouse effect in terms of the interaction of short and long wave radiation with matter. So, basically, why do we get the greenhouse effect? What is it? And how is it caused by short and long wave radiation? Pause the video. Pause. All right, I'm going to have a go now and I'm going to show you what we're going to do. I'm going to do a little diagram. So here's my lovely Earth people. Here is my atmosphere, but we can think of this as greenhouse gases, maybe. And then I have my sun. And essentially, the sunlight sends out high frequency. Notice my wave, the peaks are very close together. High energy, high frequency radiation is coming down. It hits the earth. What happens is some of the energy is absorbed into the earth so that when it bounces off, the peaks are further apart. This is long wave radiation. Now, long wave radiation cannot penetrate, no diddy, the atmosphere because of the carbon dioxide. So is reflected by the carbon dioxide back to the earth and gives it a secondary heating. Now, do you have to talk about that? No, you can just say warms the atmosphere. It's absorbed by the CO2 and warms the atmosphere. So there's 2 kind of ways it works. Some of it is reflected off the greenhouse gases and rewarms the earth. Some of it is absorbed by the COO bond in the carbon dioxide molecule. But I want to put that into words. So I'm going to say in words, short. Does that look like short? Skioret. Short, did it? Wave radiation passes through the atmosphere. My days. Look at the way I've spelled radiation. Just take me forever. This is what's so annoying. Radiation. So annoying. Right. It'd be so much nicer if it just automatically typed what I said. So shortwave radiation passes through the atmosphere, reflects off the Earth. Some energy or of the wave is absorbed. Some of the wavelength or energy, sorry, not the wavelength. Some of the energy is absorbed into the Earth, warming it. Hey, and look, I've done it again. ERAF. Okay. It is now longer wave radiation. This cannot penetrate atmosphere. I'm going to give up. I'm going to just shoot myself in the head. This cannot penetrate the atmosphere, so it can't get back out. Is absorbed by CO2 molecules in atmosphere, warming the atmosphere. And that is the greenhouse effect. Alternatively, on my diagram, I have said the long wave radiation is re-reflected or re-radiated back to the Earth. I could have said re-radiated. I don't know if there is a word as re-reflected back to the Earth and warms again. So you kind of get a double warming, right? Or you could just talk about it being absorbed by the carbon dioxide molecules. And it's really to do with the bond, the carbon dioxide bond. If you draw carbon dioxide has this bond in it. It's the double bond, and it is the perfect. This vibrates at the perfect frequency to allow it to absorb radiation. So it's like, oh yeah, baby, and it absorbs. The carbon dioxide will absorb that radiation and warm the atmosphere. And it's all to do with what type of chemical bond is inside it. But anywho, I would really give you the marks for saying shortwave radiation can penetrate the atmosphere. When it hits the Earth, it becomes long wave radiation and can no longer penetrate and is reflected back to the Earth to warm it again. Or you could say is that the long wave radiation is absorbed by the carbon dioxide molecules. The short wave radiation isn't. It's high energy enough to penetrate through the atmosphere. Anyway, guys, that's the end of the test. You know what they say? They don't say anything because hardly anyone's watching. But you know what I say, sharing's caring, hit the like, punch up the bell, subscribe. Let's get to the marks.